Thank you, Hugo. Do you see my screen and full screen?
Correct. Yes.
Yes. Okay. So thank you very much. As already introduced, Hugo, my name is Florian Baumann, and I'm working as a CTO focused on automotive and AI use cases at Dell Technologies. And today I'm speaking about the role of data in visual recognition for ADAS development. And if I'm talking about AD, I'm referring to autonomous vehicles. If I'm talking about ADAS, I'm talking about advanced driver assistance systems. So I'm also sharing the computer sound because I will introduce you and kick off this presentation with a great video. We've already seen the great example from Katalin focused on object detection. And this is a perfect example of that the future of autonomous vehicles strongly depends
Your,
on.
your audio, the video is very high.
Was there a question?
Yeah. Yes. The audio of the video is very very high.
Very loud.
Yes. Very loud.
Okay, let me stop sharing the computer sound. Um, so the future of autonomous vehicles strongly depends on visual recognition algorithms developed using real-world computer vision examples, as we can see right now in the video. And this is focused on object detection and object classification. And it's important to understand that when we are designing and putting together computer vision into production and also visual recognition, that the engineering teams and also the IT teams must work hand in hand together in considering the right scalable and efficient infrastructure in setting this up. So for example, to allow data scientists to implement these algorithms. And you would require compute, storage, networking, required to run these advanced visual recognition algorithms. What you will also require is a machine learning algorithm and in general, artificial intelligence. Of course, it's based on human teaching and on training all these models. And we can focus on various tasks out of the visual recognition area, such as object localization and detection, as we've seen in the example from Katalin, and also in the video teaser that I've introduced you to. But it's also applicable to focus on so-called semantic segmentation. And in this use case, we are trying to detect each pixel inside of the image. As you can see right now, this is a vehicle and the whole shape of the vehicle is detected. This is a tree, this is a road lane marking, whatever. And also additional use cases out of the visual recognition domain in ADAS are focused on road lane marking and in general on the extraction of metadata out of the image. So this is a car, it's 15% occluded and the direction is around 52 degrees orientation. In the traditional approach, we have to train this model. We have to teach this model as it is a small baby, for example. So you would require labels and the data itself. And typically in the traditional approach, you are extracting some features out of the image and you're throwing these extracted features and labels into the machine learning algorithm in order to train your system and then to detect unknown objects that haven't been seen by the algorithm before. This is called the learning process. And in the classification process, so remember the video that I've introduced you to, this is the perfect example of a detection and classification process. You are taking some new data, you are again extracting some features out of the data, and then you are throwing everything into the machine learning classifier. And the machine learning classifier is then detecting if this is a vehicle, a pedestrian, a road lane marking, or a cat, whatever you've trained the system on. The second process that we have right now in the automotive industry is focused on the training of convolutional neural networks. And I've also added the example of image classification. So you could use a bunch of pre-trained networks, and that you are only need to train the fourth or the fifth layer of this network, because it's already pre-trained. For example, you can take the AlexNet or the ResNet. The video that I've shown to you in the beginning is based on the ResNet. So it's a pre-trained machine learning model. And what we also see in the industry is that the visual recognition accuracy is steadily improving. So this chart introduces you into the classification error rate based on some public data sets from 2010 to 2017. And 4 years ago, we've already hit to the goal of being better than a human. So you can see that the neural networks that have been trained 4 years ago will easily compete against human. And if I clearly remember, this public white paper was published by the face detection system from Facebook. It's publicly available, and more faces are detected by using a convolutional neural network than a human could detect. And this is clearly amazing. And now let's think about um, uh, the performance of systems that get trained today. Okay, so let's go back to the automotive industry, and especially to the development of ADAS systems. Visual recognition is a challenging task, because these algorithms must be capable of dealing with different weather conditions and illumination conditions. So they must be robust against different changes in the weather or the illumination. These algorithms must also be capable of recognizing a 3D shape, as we've seen in the example, and that the algorithm detected the orientation of the vehicle. They have to also be able to differentiate between different objects, cats, dogs, everything that we have in a scenario. We have to be able to measure the relative velocity of vehicles that are driving in front of us. And we have to also detect vehicles, pedestrians, and all obstacles in a range of up to 500 meters. So we have to deal with different resolutions of cameras. And last but not least, we have to be robust against different illumination conditions, such as the camera should work at night, at sunset, sundawn, under glare conditions. And this is very often not really possible by simply using a camera or a LiDAR. And both systems are the perfect example for visual recognition. A LiDAR is a laser scanner. So each of these sensors has its own specific advantages and disadvantages. A radar is performing quite well under different weather conditions if we have some snow outside. And a radar is also easily capable of measuring the relative velocity due to the Doppler effect that we can extract directly out of the radar signals. And the radar works perfectly at night under sunny conditions, or so dark and glare performance is not really affected. The LiDAR is quite well in detecting the 3D shape of an object, and it's also working quite well at night and under glary conditions, for example. But the LiDAR is not performing very well if you have some dust outside, because these laser beams are getting reflected by some small particles inside of the air, so that you're getting a very bad image. And last but not least, we have the camera that complements the LiDAR and the radar in being superior in object classifications and in detecting objects in different ranges and resolutions. But the camera is affected by conditions. For example, if you're running the LiDAR at night, or the camera is affected by different weather and environmental conditions. So it's important to understand that we don't really have one sensor to cover all the requirements. you have to use a combination of different sensors, and the automotive industry is also moving over to thermal imaging devices in order to get another sensor in place, and also ultrasonic sensors. So we've conducted a huge AI benchmark on a real use case. We've increased the dataset size by 557 times, and we focused on semantic segmentation, and that we've assigned a value to each pixel. Take a look to the image in the upper right corner. And we focused on a traditional object classification use case, and that we've detected pedestrians, cars, trucks, convertibles, traffic signs, everything that's on the street. We've used around about 1 million images. So overall, 2.6 million images for both benchmarks. In this example, we've used 64 Tesla V100 GPUs and around about 1 petabyte of our all-flash storage. So semantic segmentation, as I've already pointed out, is one of the most challenging computer vision tasks that we have out there, because we have to assign a pixel to each value in that image. If we are dealing with 2K or 4K images, we have to classify 400,000 of pixels out of one image. And this is quite complex and quite challenging. And I've also introduced you earlier into the object detection and object classification benchmark or video that you've seen in the beginning. So in the semantic segmentation use case, as mentioned earlier, we are assigning a pixel to each, a value to each pixel inside of the image, and that we could detect the 3D shape or the contour of a person, for example, or of a vehicle. So as mentioned earlier, we focused on two different use cases. The first one, semantic segmentation, the second one, object detection. And we've demonstrated that we are able to push 1.6 million images in 4 minutes and 25 seconds through the platform. This is clearly outstanding. We've also demonstrated a linear scalability from 4 to 64 GPUs. So you are able to train a self-driving car algorithm, a machine learning algorithm in 4 minutes and 25 seconds, being able to detect all vehicles and performing a semantic segmentation on the data set. So last but not least, and this is one of my last slides, we've published our new so-called Dell autonomous drive ecosystem in December 2020. And this autonomous drive ecosystem is clearly focused on visual recognition tasks, because the underlying sensors used in the data collection building blocks are cameras, up to 13, LiDAR, radar, ultrasonic sensors, thermal imaging stuff. And then you can follow the whole process around the start of production. And very interesting for you guys is the building block around data curation, that we are collaborating with companies who are able to identify valuable training data and sorting this training data into two different boxes, lower relevant data and highly relevant data. The company name is Slightly. Check them out. It's really great. A visual recognition startup out of Switzerland. And also interesting for you is the building block around scenario extraction, and that we are trying to extract interesting scenes out of the image, such as an unprotected left turn, an unprotected right turn, the cars in a tunnel or in a roundabout. So interesting corner cases and edge scenarios that are needed in a later stage of the development workflow to train the algorithms. And then, of course, we are also focused on data labeling, data annotation, data quality augmentation, and also data compression, because camera images are the most hungry data type that we have out there, because it's so complex. So companies are focused on how to compress this data in order to speed up development life cycles and also reduce the time to market. And then we have on the right side companies focused on simulations, synthetic scenario generations, and that we are using techniques out of the gaming industry in order to feed the algorithm with more data, visual data generated synthetically, to speed up the development time. So that's it from my side. Thank you very much, and back to Hugo.